for part 2. So here's part 2. So we're going to graph f of x equals x plus 3 over x squared minus 2x minus 15, okay? So this is going to be one of those graphs with asymptotes. Remember we talked about that? It's going to be one of those weird graphs that has asymptotes. So it's going to be, first thing I'm going to do is factor. I'm going to rewrite it so it's x plus 3 over an x minus 5 and an x plus 3. Okay, I'm going to do that first. Just factor wherever you can, okay? Because it tells me two things. Can't divide by 0, right? 0 on the bottom is bad. 0 on the bottom is bad. So it tells me this. It tells me that I have an asymptote. I have a vertical asymptote at x equals 5. Right there. Because 5 minus 5 is 0. You can't divide by 0. It's a vertical asymptote. It can't be negative 3, but negative 3 is removable, right? So if I can cancel out the problem, removal means if I can cancel it out, right? See cancel, cancel? If it's a removable problem, it's a hole. So I have a hole at x equals negative 3. Mr. Massey is going to want you to know this. Now the coordinate of my hole is this. If I cancel out, if I remove the problem, it would look like this. Right? Cancel, cancel. And if I plugged in negative 3 right here, I'd have 1 over negative 8. So my hole is at negative 3, negative 1, 8. That's the coordinate of my hole. I'll do it again. After I get rid of the problem, I can plug in negative 3. I can put negative 3 right in here without dividing by 0. Negative 3 and negative 5 makes a negative 8. So my hole, the coordinate of my hole is at negative 3, negative 1, 8.
Wait, where did you get the 1 over x minus?
Right. So x plus 3 over x plus 3. Anything over itself is 1.
Oh.
10 over 10, 5 over 5, right? So that's my hole, right? So a couple of things I know. I also know my horizontal asymptote is at 0, because if I do my gobble up and I go to infinity, I'd have really infinity over infinity squared, right? Which is 0. So I also have a horizontal asymptote at y equals 0. So I'm sure that most of you are already going to be using your calculator to graph this, but I don't need a calculator. I can do this without a calculator. I do know that I'm going to have a hole at negative 3, negative 1/8, about somewhere about there. I'm going to make a hole. I'm going to have a vertical asymptote at 5, so at 1, 2, 3, 4, 5. At 5, I'll have that right there. I know I have a horizontal asymptote here. I have a y-intercept. You ready? I'll show you real quickly. I have a y-intercept at negative 3/15 or negative 1/5. Do you see it? X is 0. X is 0. I got a y-intercept of negative 1/5. Okay. So negative 1/5 is my y-intercept, which is about here. And I kind of know that my graph is going to look like this. And it's going to come here. And once it crosses this way, it's going to start approaching that asymptote, right? It's going to approach that asymptote. I know it goes, bounces over my hole, goes through my intercept, and then it's going to start heading towards that asymptote. It's just going to take a dive, right? And then the other half of the graph is up here. And same thing, the other half of the graph is bound by the asymptotes. Now, you might be saying, well, I want to check it. I'm not sure. It's a test. I'm going to look at my calculator. So let's look. So if you want Desmos, yeah, you got to use a laptop from Mr. Bart, okay? So if I want to go ahead and check it, I just graph it. I go, okay, what is x plus 3 divided by x squared. Don't forget parentheses if you graph minus 2x, subtract 15, and if I graph it, boom, looks like just exactly what I graphed, doesn't it? Doesn't that look like it? If I change my window a little bit more x's, there it is. Boom, boom. Hey, looks like just exactly what I put down. Okay? Man. Okay. So then, real quick, what is the vertical asymptote? We know the vertical asymptote was at x equals 5. What's the chord of the hole? We know the hole's at -3, -1/8. What is the equation of the horizontal asymptote? It's y equals 0, right? Because we gobbled up and we got 1 over infinity, which is 0. Okay. Finally, almost done. 15. Am I going too fast? Okay, 15. We'll finish this up. We'll be done. Okay, 15.
Wait, what about 16?
Didn't I do? Well, we'll do 16 too. 16 is not that hard. We'll do 15. Okay, so find the equation if y varies jointly as the square of x, the square root of x, my bad. I can read square root of x and the square of z. I'm going to put a k right here. And we got to find k, right? When z is 2, x is 25, and y is 5. Okay, we can do this. We're going to go 5 equals k times the square root of 25 times 2 squared. 5 equals k times 5 equals, thanks Zoe, 5 equals k times 5 times 4. 5 equals a 20k. Divide by 20 and I get 1/4 for the value of k. Am I going too fast? So my equation is y equals a 1/4 square root of x times z squared. That's my equation. Now, do I need to do anything with it? Nope. But I might ask you tomorrow, okay? I might say then if blah, 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 find y, okay? Okay, 16. Last but not least, we're going to make it. All right, 16. A lot of words, but let's see if it makes any sense, okay? Okay, the weight of an object above the surface of the Earth varies inversely with the square of the distance from the center of the Earth. Okay, what the heck? Okay, we know this. Think about space. Think about the moon. Think about planets. The further away from Earth they are, the less they weigh. There's less gravitational pull. That makes sense? So, in fact, how much? The inverse of it squared, okay? So, on 16, let's start with this. The weight of an object varies inversely to the square of the distance, d squared. Okay, how's that for an equation? Does that make sense? Okay, now we got some information. So if somebody weighs 150 pounds, that's a weight, then they're going to be a distance of 2,900 feet, okay? So they might weigh more on Earth, but out in space that far away, that's what they weigh, okay? So let's find K. All right, I can do that. I can go 150. Huh? Yeah, thanks, Landon. So let's plug them in. Let's put 150 for weight. Let's put 2,900 squared for D. Multiply that up, right? Use a calculator. 150 times 2,900 squared equals K. All right, I'm going to use a calculator. Heck yeah. Okay. 150 times 2,900 squared. I'm going to get a big number. Woo, that's a big number. 12615 1 2 3 4 5. 1 2 3.
Oh, squared.
126,150,000 is the value of K. That's my constant variation. Yes.
I got a different answer.
Did you forget to square it?
No, I squared it.
I got
No, not you.
8,410,000.
Oh, you put the thing in the wrong place. 1, 2, 3, 1, 2, 3, 4. You messed up your commas.
Oh, yeah, you did mess up.
Did I mess up my commas?
Yeah.
1 2 3 4 5. Oh, yeah. Thanks, Zoe. I did. 1 2 3 1 2 3. All right. So it's one. Is that 1 trillion? Woo, that's a big number. No, 1 billion. My bad, 1 billion. But that's just a constant variation. So my equation is going to be this. You ready? W equals this big number, 1 1,261,000, nope, 1,261,500,000 all over my d squared. That's my equation. Okay, now, I'm smart enough that I'm going to leave that number in my calculator because I'm going to need it. Okay, don't erase your, because I don't want to retype that, okay? I'll leave that number in my calculator. So the last thing I'm going to do is use this equation. So, okay, now, somebody's 6,000 miles. So if d is equal to 6,000, right, miles from Earth, what's the weight? Well, that's easy. I'll just plug that in. So let's say the weight is equal to 1,261,500,000 divided by 6,000 squared. I'm just going to use my calculator. I'm going to go this number divided by 6,000 squared. And I get 35 pounds. Wow, they don't weigh much. They're a long, long ways from Earth, aren't they? 35 pounds. You're almost floating in space, right? Because at some point in time, you're weightless. Does that make sense? This actually makes sense. Because we know when we escape Earth's gravitational pull, we start to float, right? We weigh nothing. Okay, that's all I have. So, no, I won't